Yesterday we introduced the topic of a homogeneous ODE with constant coefficients. We solved homogeneous ODEs by guessing a solution of the form y equals e to the rx. We then plugged this solution into the ODE to determine the values of r that would correspond to actual solutions. Yesterday we focused on the case that when we solved for r, we got distinct real values of r. We didn't get any repeated solutions, and we didn't get any complex solutions. Today we're going to deal with the case that our auxiliary equation does give us repeated r's or does give us some complex r's. First, let's tackle the case where our auxiliary equation has complex roots, and to see how such a thing might occur, let's consider the ODE y double prime plus 9y equals 0. If I guess a solution of the form y equals e to the rx, then plugging that guess into this equation will give us the auxiliary equation r squared plus 9r, r squared, 2 r's for y double prime, and then 9 with no r's because of no primes equals 0. So from this we get r squared equals negative 9, which does not have any real solutions, but which does have two complex solutions. The imaginary number, usually represented by a lowercase I, is a shorthand or stand-in for the square root of -1. There are no real numbers whose square is -1, so I is called imaginary. Imagine that there is a number whose square is -1. We can use the imaginary number I to represent the imagined solutions to the equation r squared equals -9. This would be the square root of 9, which is 3, times the square root of -1, which is I. So based on our guess, our solutions would have the form y1 is equal to e to the positive 3i times x, and y2 equals e to the negative 3i times x. But the problem is that these formulas are complex valued. They have the imaginary I in there. And we would prefer to get solutions which are real valued, where all the inputs and all the outputs of the function are real numbers. So what we're going to use is the fact that if you take e to the power I times something, maybe I'll just call it I times w, then that's equivalent to cosine of that w plus the imaginary number I times sine of that w. This is a consequence of looking at the Taylor series for e, cosine, and sine. So based on that, our first solution y1, which is e to the I times 3x, would be equivalent to cosine 3x plus I sine 3x, and our y2 would be equivalent to cos minus 3x plus I sine minus 3x. Now if we use the fact that cos is even and sine is odd, we can rewrite y2 in a little bit of a slightly different way as cosine 3x negative I sine 3x. So what I'm going to do now is I'm going to take these two complex solutions y1 and y2, and I'm going to combine them in such a way that I will hopefully be able to eliminate the imaginary part from these expressions. For example, suppose that I construct a new solution y1 tilde by taking half of y1 and adding it to half of y2. We know that if we take a linear combination of two solutions, we're going to get another perfectly valid solution. But it turns out when you add these two functions together, the plus I sign and the minus I sign will cancel out. The two coses will combine, and the half will turn it into just cos 3x, which is a real solution. Likewise, if you multiply y1 by the constant 1 divided by 2i, you multiply y2 by the constant negative 1 divided by 2i, and then combine those, this will give you just the sine portion, real valued. So in answer to this question, what are the solutions to this differential equation and only real valued solutions are allowed? I would say that these solutions are of the form y equals number times cosine of 3x, the real valued solution that I constructed, sine of 3x, the other real valued solution that I constructed. The general solution to the differential equation is of this format, assuming that only real valued solutions are allowed. Now, to sum up what we just did, suppose that we have a homogeneous equation and we find its auxiliary equation has complex roots alpha plus minus beta times I. In that case, your two linearly independent real valued solutions are given by y1 is equal to e to the alpha times x, alpha being the real part of your complex root, times cos beta x, beta being the part attached to the I. And the second linear solution is the same except with sine beta x. For example, let's try and solve the ODE where we have 3y double prime plus 2y prime plus y equals 0. So here's my auxiliary equation. 3r squared plus 2r plus 1 equals 0. So the solutions are, by the quadratic formula,
x is equal to negative b.
Negative 2 plus minus the square root of 2 squared minus 4ac all over 2a, which is equivalent to negative 2 plus minus the square root of minus I over 2. Now, because we have a negative 8 under the square root, this quantity is going to be complex. The values of r will be equal to, after simplification, negative 1 plus minus the square root of 2 times I over 3. Or, put another way, negative 1/3 plus minus the square root of 2 over 3 times I. Now, in the language of the above theorem, the number called alpha would be this minus 1/3, the number that is not attached to any I values. And in the language of the theorem above, the number attached to the I would be what we call beta. So based on the above theorem, our two linearly independent solutions would be y1 equals e to the alpha times x, cosine of beta times x, y2 equals e to the alpha times x, sine of beta times x. And therefore, our general solution to this differential equation would be that the function could have the form c1 e to the negative 1/3 x cos root 2 over 3x plus C2 times the other solution with the sign. So that is how we solve a homogeneous differential equation in the case that we have an auxiliary equation with complex roots. Simplify the complex roots and identify the value of alpha, which is the real part, which is not attached to the I, and the value of beta, which is the complex part, which is attached to the I. Then use that alpha and that beta to construct our two linearly independent solutions according to the rule given in the theorem above, e to the alpha x, and then cosine of either beta x or sine of beta x. Then use those two solutions to build up our general format for any solution to the differential equation. We can also do this in initial value problems. In this initial value problem, we're given the ODE y double prime plus y equals 0. We require that y of pi over 3 is equal to 0, and y prime of pi over 3 is equal to 2. So as always, we're going to start by finding the general solution to the differential equation. So I'm going to pass to my auxiliary equation. So y double prime gets replaced by r squared. Y with no primes gets replaced with just a 1. So r squared is equal to negative 1, and therefore r is equal to positive or negative the square root of minus 1. Therefore r is equal to positive or negative I. In this case, the value of alpha, the number which is not attached to any i's, is equal to 0. And the value of beta, the number which is attached to I, is just the constant 1. So our two solutions would be e to the 0 times x, cosine of 1 times x, but of course this can just be written as cosine of x. And likewise y, 2, would just be sine of x for similar reasons. What therefore is our general solution? Our general solution would be c1 cos x plus c2 sine x. So now they say to me, alright, I have two requirements. First of all, when you plug in pi over 3, I want the result to be equal to 0. Second of all, when you plug pi over 3 into the derivative, I want the result to be equal to 2. So taking the derivative, I get negative c1 sine and positive c2 cos. Now if I plug pi over 3 into the original function, then I get c1 times 1/2 plus c2 times root 3 over 2. And if I plug pi over 3 into the derivative, then I get negative c1 times root 3 over 2 plus c2 times 1/2. And this is the system that I need to solve for c1 and c2. So this looks like a good opportunity to use substitution. For example, if I take the first equation and rearrange it, then this tells me that c1 is equal to negative root 3 times c2. And if I substitute that back into the second equation, then that tells me that 3 over 2 times c2 plus c2 times 1/2 is equal to 2. This implies it looks like 2c2 is 2, and therefore c2 is equal to 1. And based on that, if I plug that information back into this red equation, then I find that c1 must be equal to negative root 3. So all in total, I find that my solution must be equal to negative root 3 cos of x plus 1 sine of x. That would be the solution to this initial value problem. So the other situation where some trouble can be caused is the case when the auxiliary equation has a repeated root. To give you an example, let's consider the ODE where we have y double prime minus 8y prime plus 16y equals 0. In this case, our auxiliary equation would be r squared minus 8r plus 16 equals 0, which factors as x minus 4, x minus 4. So we get the one solution, x equals positive 4, which is repeated twice. Because I only have one value of r, I only get one solution, which is not enough to build up the set of two linearly independent solutions, which I need in order to describe the complete set of solutions to this second order differential equation. So let's try and figure out what the second linearly independent solution would be. Now, when you know one solution to a differential equation and you want to find the other solution to the differential equation, the technique that we introduced a few days ago was to try reduction of order. So I'm going to go back to my differential equation. I'm going to verify that y double prime stands alone. And then I'm going to note that the function p of x in the notation of the reduction of order shortcut formula would be the function negative 8. So that tells me that u prime would be equal to e to the negative integral of negative 8 dx divided by our first solution, quantity squared. Now this can be simplified. In the numerator, the integral of negative 8 would be negative 8x. So because of that second negative sign, it would change to e to the positive 8x. Meanwhile, in the denominator, e to the 4x squared would be also e to the 8x. So u prime, in the language of the reduction of order formula, u prime would be equal to 1, which implies that u itself would be equal to x. And therefore the second solution that we need to complete the set is equal to x times the first solution, or x times e to the 4x. Now, to sum up what we found in the previous exercise, we have the following theorem. Suppose that your auxiliary equation to a homogeneous ODE has a root of multiplicity k. Then you can create a set of k linearly independent solutions by taking e to that value times x, taking x e to that value times x, then x squared, and then go up to x cubed and so on, until you have a number of solutions which is a match to the number of times that that number showed up in your auxiliary equation. For example, in the previous problem, r equals 4 showed up as a solution of multiplicity 2 in our auxiliary equation. A multiplicity 2 because r minus 4 showed up 2 times. So I was able to construct two linearly independent solutions, one from e to the 4x, and the next one by sticking an extra copy of x e to the 4x. For an even more dramatic example of this, let's consider the ODE, which is third order, y triple prime plus 3y double prime plus 3y prime plus y equals 0. In this case, our auxiliary equation would be r cubed plus 3r squared plus 3r plus 1 equals 0. Now this can be factored as r plus 1 quantity cubed equals 0. R plus 1, r plus 1, r plus 1. So r equals -1 is a solution to the auxiliary equation, which is repeated and has a multiplicity of 3. So that means that I can cook up 3 linearly independent solutions. y1 is equal to e to the -1 times x. To get y2, just stack an extra x onto that solution, and for y3, just tack another extra x onto that solution. Then we can get our general solution, c1 e to the -x plus c2 x e to the -x plus c3 x squared e to the -x. That concludes today's material. We now know exactly what to do with all possible cases of a homogeneous equation with constant coefficients. If the auxiliary equation has distinct real roots, then that's really easy, because the distinct real roots are going to give you distinct linearly independent solutions that you can use to construct your general solution. If your differential equation has complex roots, then you need to use the formula given in this theorem to convert those complex roots into 2 real-valued solutions, which contain cosine and sine. And in the case that your auxiliary equation has a repeated root, then you can construct linearly independent solutions by just sort of tacking on extra factors of x to get other solutions which are linearly independent from the ones before.